Welcome to Zero Knowledge, a podcast where we explore the latest in blockchain technology and the decentralized web. The show is hosted by me, Anna.
And me, Frederick. In this episode, we sit down with Marek and Kobi from Celo to talk about their blockchain and how you can use zero-knowledge proofs to construct ultra-light clients.
Before we start, we want to say thank you to this week's sponsor, Aragon One. Aragon One is working to make decentralized autonomous organizations, or DAOs, easy and accessible to create and manage. If you love working with talented designers building smart user interfaces, or if you're simply excited about DAOs, then you should check out Aragon One's available jobs. The company is currently hiring a front-end engineer to help build the platform for modern organizations. For more about the front-end engineering role, or other available jobs in general, check out aragon.one/jobs. That's aragon.one/jobs. So thank you again, Aragon One. And now here's our interview with Marek and Kobi from Celo. So today we're sitting down with Marek and Kobi from Celo, and we're going to be talking about light clients, how zero knowledge could potentially be used to make light clients lighter, and why this would be desirable. Welcome to the show, guys.
Thanks. It's great to be here.
Thanks.
So maybe to kick off, what is Celo?
So Celo is a permissionless platform that makes financial tools accessible to anyone with a mobile phone. And I think what makes us maybe a little unique is our product-focused approach. And so we're very focused on end-user usability, and we're very focused on financial inclusion. And so that means that we go out, we've done a lot of user research. We've done over 150 user research studies in the field in around 10 countries or so. And we've used that to guide our work, oftentimes synthesizing that research and taking it back to the team, and then using that to guide the development of the protocol. And I think what's interesting with this approach is that we learned really early on that we had to develop in a full stack manner. We knew that to reach our target customers, we needed to build for mobile, and to deliver a great mobile experience, we had to build in a manner where we were building both the platform and the mobile app on top of that.
Where does the light client come in to this exactly?
Yeah, and so to deliver a great mobile experience in a fully permissionless, censorship-resistant manner, it's important to have a very good light client protocol. And so I think there's been a lot of work that the Bitcoin community, that Ethereum has done to really bring us to a point where light clients are, I think, feasible, but they still require too much data to be actually practical in day-to-day use. And so one of the innovations that Celo has done is to create a light client protocol that requires only just a trickle of data while remaining fully censorship resistant.
I really want to dig in more into sort of how you've built a lot of these things, because I think that's an interesting and somewhat unique story and ties into the light client stuff as well. But maybe before we go in there, what about you guys? Where are you coming from and how did you get to this space?
I'm an entrepreneur. I have a background in computer science, did my undergrad at the University of Toronto, and then later went to MIT for my PhD. And at MIT, I met Rene, who's one of the co-founders of Celo. And back then, in a class taught by Tim Berners-Lee, we created our first company called Loku, which was in the semantic web linked data space. So some of you might recognize that was actually the original Web3. Tim Berners-Lee was looking to do to data what he did to documents, namely make them interconnected and accessible to everyone. And so we ended up actually starting a company around linked data. As is, I think, common with startups, we kind of pivoted towards becoming a machine learning company that was helping small businesses better compete against the Amazons and the McDonald's of the world through data. And that company did well. It got acquired a couple of years later. And it was actually, I think, the weekend after we got acquired that I was at Outside Lands, and Brian Armstrong actually showed me the Coinbase app on his phone and actually sent me my first Bitcoin. And so that was pretty exciting.
That's how you got into it.
What about you, Kobi?
So I got into Bitcoin, I think, around 2013. I was doing my master's at the time, applied math. And I just had to give a seminar about any subject that has math in it. So I heard about Bitcoin a while before, and it fascinated me. So I just gave a seminar about that. And since then, I couldn't leave it. So that's, I think, how I originally got into it. I got involved in Ethereum later on, I think in early 2015, a bit before Olympic, I think. Yeah, and later on, I think in 2016, I heard about Zero Knowledge, about what Zcash was doing, and I started experimenting with it, working with it, and also tried out like proofs of replication that has been designed by that point. And that's how I got into leading a team of ZK Snark developers for a few years in Kedit. And after that I met Marek.
We actually met at the ZK Proof Workshop. Which is a good place.
Yeah, we met at ZK Proof. That's true.
What role do you guys take in the company in Celo?
Yeah, so I'm the CTO and one of the co-founders of C Labs, which is one of the kind of companies working on Celo.
I'm in C Labs leading the cryptography effort.
Nice. Kobi, would you say, are you like on the research side, or are you also doing some engineering?
Actually, I'm doing a lot of engineering
and
some research.
Cool.
So you were talking about Celo and sort of being mobile first, being focused on usability. It's kind of obvious that, obviously usability is good, but why did you decide that these things should be your goals? Like, how did you come to that point where, mobile first is a requirement for us?
Yeah, I think it comes down to our mission. So Celo's mission is to create a monetary system that creates the conditions for prosperity for all. And everything that we do is kind of in service of that mission and just in service of advancing financial inclusion. And so for us, even though we're very, very excited by kind of crypto and blockchain technology, it's really a means to an end and not an end in and of itself. And so when you take this kind of viewpoint, you kind of naturally end up really focusing on the end users.
And I think that ties into what I was talking about with how you've built things. So this is not something that we've talked about yet, but you actually forked the Geth code base and started modifying that. So you didn't start building everything from scratch. Why did you make that choice?
So I think we initially started by trying to build on Ethereum to create a great mobile experience that could kind of meet the needs of our target users. And throughout that effort, we struggled to get to an experience. This was around 2 years ago. I think before people were doing a lot with meta transactions, and generally, I think also maybe when CryptoKitties was really driving the price of gas up. And so it was really hard for us to build that experience that we wanted to. And so we knew that we needed to build our own kind of layer one platform at that point. And we had a choice to start from scratch or to invest more effort on usability, on the mobile wallet, on the light client protocol, and not built from scratch. And, I think at the time, the decision to start with Ethereum was obvious. 2 years ago, it was, definitely the best starting point for us.
Why did you choose to fork Geth and not Parity?
Yeah, that was a really hard one, actually. We were looking at both very closely, and I think the big reason was just at the time, Parity was not compiling to the mobile platform yet and didn't have a version that we could link into a mobile application. I think that's changed, obviously, since then, but as we made changes to our consensus protocol, as we made changes to the light client protocol, it meant that bringing parity up to the place that we were with Geth currently just takes more effort than we have time for. But it is a hope of mine that we can actually do that. I think having 2 clients running on a network, I think is just, there's a lot of goodness that comes from that. And so I think it's definitely near to our hearts. And
does that mean that is the majority of your stack built in Go?
Some of it. So actually a lot of our protocol we ended up building in what we're calling system smart contracts. So Celo is a proof of stake protocol. It has a lightweight identity system that makes it easy for users to find each other by phone number. It has a stability protocol that allows you to send stable value easily to people. And it has full on-chain governance for all of these system smart contracts. And all of these are written in upgradable smart contracts that, in effect, can be upgraded through governance and only through governance.
But are these is it also kind of using a Solidity-like language to write the smart contracts on a Geth-like client?
Exactly.
Okay.
Yes. So much of the protocol is written in Solidity. And then we do have changes, obviously, at the Geth layer as well. We have, for the proof of stake protocol, we run a protocol that's somewhat similar to Cosmos, where we, through people staking the native coin on the platform, which is Celo Gold for us, can elect 100 or possibly more at the time of network launch validators that then perform PBFT consensus. And this is really nice because it allows for very short block periods. It allows for 1 block finality. And it allows for this really interesting and new light client protocol that we've created.
Cool.
So the changes you've made if you just talk about the client itself, there's obviously a new consensus algorithm that you were talking about, but then you've done a bunch of other things in Solidity, so that doesn't require, layer 1 changes. Is there anything else notable aside from the light clients, which I think we should talk more about, that you've made, changes you've made on layer 1?
One thing that's actually not in the layer 1, but I think we're really excited about at Celo is the addition of a lightweight identity protocol that maps hashes of phone numbers to public keys. And so this is in effect, a decentralized PKI that allows people to find each other more easily and communicate securely and transact securely just by knowing each other's phone numbers. And so I think for the mobile first use case, the usefulness of this might be pretty obvious. When you're sending a transaction using Celo's mobile wallet, you can send that transaction simply by looking up people in your contact list, looking up them by phone number. And I think perhaps even more interestingly, this allows users to send transactions to people before they even sign up. And so if you have a friend who isn't yet on Celo, and you have 10 maybe Celo dollars or Celo shillings that you want to send their way, because we have this decentralized phone verification protocol, you can send that payment to an escrow account, which is locked such that the user can only withdraw from that account after they've verified their phone number. And so this allows for a flow that looks very similar to what you've seen on centralized services like Venmo or PayPal. But it's fully decentralized and trustless. We've made a number of changes that are, again, maybe not surprisingly, really focused on usability. And so early on in our research, we learned that the complexities of owning multiple assets to pay for gas was a big hurdle for our target audience. And so
I guess what you mean by that is using one token or transferring one token but having to pay gas in another?
Exactly.
Okay.
And especially if that gas currency is a volatile currency and the price of gas changes, frequently over time, this presented a pretty big hurdle for usability.
And this is a pain in the ass for most people. I mean, if anyone has gotten a bounty from a Gitcoin bounty or something, that's paid in DAI. And then you have DAI sitting in an account that you can't move anywhere because you don't own ETH.
Yeah.
Exactly. And so one of the changes we made fairly early on is to support paying for gas in multiple currencies, including in ERC20-like tokens. And so this means that if you want to send one of our stable coins, like Celo dollars, you can pay for that transaction fee in Celo dollars. And so when it's displayed to you as something for you to confirm, it's in the same currency. You can kind of calculate the percentage in your head if it makes sense for you. And it's just much, much more intuitive.
But this is still what you're talking about here, like ERC20-like tokens living on the Celo network.
Exactly.
There's no real connection between like the existing Ethereum main chain and Celo right now, is there?
There is not, but we are working hard to add a bridge. And so one way to think about Celo is potentially as an extension to the Ethereum ecosystem, mostly because we plan to have ETH in the reserve that backs the stable coins.
Okay. Oh, interesting. So it'd be like a cross-chain stablecoin.
That's right. And early on, some of the ETH might be off-chain managed, but the plan is longer term to have it be fully automatic with cross-chain rebalancing.
So this already sounds like it's a very ambitious project already. You have your own protocol, your own sort of tokens and ERC20-like tokens sitting on that protocol, a stablecoin, a POS system, and then this light client construction. And maybe you have something else too. I don't know.
There are a lot of things. Full on-chain governance, full node incentives, which is another thing that we modified Geth for. So under Celo, full nodes can be incentivized to serve traffic to light clients. And so I think this is a common problem on Ethereum and other networks where there's no incentive for you to serve light clients. By default, if you fire up a full node, you won't be serving them. You have to explicitly turn that on. And as a result, it's sometimes hard as a light client to connect to a network. And so with Celo, we take this coffee house model where serving the information that you need to fetch your balance and to access the protocol is free. But when you want to transact, then you have to pay. So it's similar to being able to kind of sit at a table, maybe work with your laptop, but if you want a coffee, you have to pay for it. Okay. And we do that by modifying the transaction object to include an account that part of the transaction fees need to be shared with. And a full node can choose not to forward those transactions if they don't have their own account listed in that transaction.
That's interesting. So this is something that I've asked people to build for like 2 years, is an incentive model for light clients. But does this mean that if someone wanted to, they could modify the light client to basically just remove that extra fee?
They can, but then full nodes will likely not forward their transactions. And so they wouldn't really be able to get around it.
So when I'm sending a transaction, I'm doing it to a full node, and then they forward the transaction only if a fee to them is included in that transaction.
Exactly.
How do you prevent just gossiping the transaction generally on the network? I mean, I guess it's sort of the same answer, that no one would, like, the gossip would stop at the first stop regardless of where you send it, because it's not in their interest to forward it.
Yeah, I think if a light client pretended to be a full node, right now it's communicating using a different protocol. And so I think it's easy to for a full node to know that it's talking to a light client, but it could possibly try to fake being a full node. We're still exploring ways to mitigate that. And then in the worst case, maybe someone would be, a full node would be duped and not get paid. But that's a pretty, I think, the worst case is just a status quo today. And so that's not the end of the world.
No.
Let's really talk about this light client, because I feel like there's some interesting features about it. So I think we've spoken about light clients in the past on the show, but I think given that we're going to be talking quite a bit about light clients, it might be good to define kind of what light clients are, what they tend to be used for, how we've seen them in the past.
Light clients are clients that are typically more resource constrained, typically both in terms of storage and bandwidth, so much so that they can't participate in a decentralized protocol acting as full nodes where they have the entire state of the chain and every transaction gossip to them so that they can verify every state transition in the chain. And so to make it possible for these lighter weight clients to participate, a lot of research has been done around using Merkle tree commitments that allow full nodes to maintain the state of the blockchain in a sort of Merkle tree. And as long as these light clients have an efficient way to download and to get the latest Merkle tree commitment, they can query other nodes on the network for data and use that Merkle tree commitment to validate any data that they receive from these full nodes.
In the case of a light client, is it like I've always understood light clients as kind of proving that a block has happened, but also sort of showing the state at that moment. Is that the case, or do light clients not show the state of a blockchain?
So the light client knows what is, let's say, the latest header that the blockchain had. If we're talking, for example, about Ethereum light client, and they know all the headers that exist in the Ethereum chain, and they verified at least those. So the headers themselves contain, for example, roots of the state. And that allows light clients to request to do some queries about the state when they can ask full nodes or other nodes in the network that actually hold this state. So light clients don't have to hold all the state, but so they have to have enough cryptographic roots in order to be able to query for elements in the state such that they will still be certain that this is exactly what exists in the network and that they're not being fooled.
How would you describe this light client? Like what are the features of this light client that you think could be highlighted?
So I think the main thing that, like Marek said, we are very focused on light client. So this light client sync, we call it ultra light client sync. It's focused on light clients being able to sync really fast to the network. And to do that and serve light clients anywhere, we want to reduce the data that clients have to get as much as possible. So one of the main features of this ultra light client protocol is that you have to download a really small amount of data to get synced to the latest state in the network and to be able to efficiently making light client queries to full nodes and be certain that you're actually getting what you should be getting.
And how do you do that?
There are a few steps to this. Let's start from the end, actually. All you have to do is download a few ZK Snark proofs, and you will know what is the current state of the blockchain. And what do you care as a light client? What do you care? What is the state you care about as a light client? And that would be what is the current validator set in the network. So in Istanbul or in PBFT in general, you have a set of validators that are the validators that are approved to sign blocks. Mm-hmm. And initially in the Genesis block, you have a set of validators that's been chosen. And in Celo, each day, at least now it's each day, the validator set changes. There are votes of what the next validator set should be. That's in the governance system. And each day, this validator set changes. So a light client would, at most, need to download this last block in each day, which we call an epoch. And after they do that, they would be able to know what is the current validator set for that block. So we start at day 0, we have validator set at the Genesis block. And then after day 1, we need to download just the last block in this epoch. And we know the validator set then.
And this, by the way, gives you a 17,000 times reduction in how many headers you have to download. So this alone is already pretty substantial.
Oh, yeah. Blocks are really fast. So currently they're around 5 seconds for each block. So you would have to download a lot of blocks to sync a day. Yeah. So this would be a naive light client. A naive light client would download the last block in each epoch and they would have to sync. But this is still a lot of data to download, especially after a year passes, you have to download quite a bit of data. So we aim to reduce that even further. So the way we approach that is, first of all, we started out with signatures, with ECDSA signatures on blocks. And that means that whenever a block is authored, a majority of the validators have to sign this block in order for it to be accepted by the network. So a majority in the case of 100 validators would be more than 66. And that means that each block contains 66 ECDSA signatures. So that's something that grows really fast, and we wanted to reduce that. So the first thing we did is replace those signatures with BLS signatures. And the nice thing about BLS signatures is that they're aggregatable non-interactively. So that means that instead of 66 or 67 signatures, we can have one aggregated small signature for each block, and especially for each last block in an epoch.
Is that like did you put it in a Merkle tree? Like, how did you make it from 66 to 1?
So that's something that's really nice and native in BLS signatures themselves. Mm-hmm. There is a nice protocol that you can do. You basically add up all the signatures, and you are able to verify as long as you also add up the public keys that would verify these individual signatures. And if you run this, let's say the sum of the signatures in the normal BLS verification equation, it would still pass, and you would know that this set of public keys signed this aggregated single signature.
I think like anyone who's familiar with the ETH2 protocol knows they're also trying to use BLS signatures for the signature aggregation of validators. But you're using a different curve, if I understand correctly. You're using the 12377 curve, which is newer.
Yes.
Why did you pick that one?
That's because we still weren't satisfied with the amount of data you have to download. So we further went ahead and designed this Snark-based protocol, where instead of having to download the last block in each epoch, you just have to download the Snark proof that shows the following. Let's say we're at block 0, and we have the Genesis validator set, and we collect on the side, let's say 100 epoch blocks. And what we do, we then take them as provers. We can then take these 100 epoch blocks, the validator set that changed, or the difference in the validator set that changed in each epoch, and run this transition inside the Snark proof. Now, that would get you from knowing as inputs the validator set at the Genesis block to the validator set at block 100 without having to see all the epoch blocks in the middle. You just need like the beginning and the end, and you're good. You can be certain this is the validator set at block 100. Now, the reason that we had to not use maybe the curve that is popular right now, which is BLS 12381, is that we want to run the verification of BLS signatures inside a Snark. And that means that this curve has to satisfy some properties. It's about the two-adicity of the base field of the curve, but it's not really important. But we can just say that 381 does not satisfy that. It wasn't a design goal for 381. And actually, 381 has a bit better performance for square roots, for example, because of that, because they don't satisfy this property.
That's an interesting approach. So to recap, I mean, the main problem of a light client is to figure out what the correct chain is. And in Ethereum as it is today, it does this by downloading all the headers. Actually, in reality, it checks a hard-coded header and just sings from there. But that's undesirable for other reasons. So you imagine you have to download every header. You already make this better by introducing proof of stake, because you really only need to download the headers for where validator transitions happen to be able to verify that those are done correctly, right? So now you need to download one per day instead. And then you introduce that or reduce that even further by saying you don't have to download each state trend or like each validator transition header. You can just download this zero knowledge proof that proves that all of the validator transitions have happened correctly. Is that an accurate summary?
Exactly.
Perfect.
So in effect, you are proving the like client protocol that you would have if you didn't have these snarks.
Yeah.
And so you've some of your listeners probably are familiar with Coda, which is also using snarks to prove not just headers, but entire blocks and entire transactions inside those blocks. And so one way to think about the difference between these two approaches is in Coda's case, you're again proving every transaction, you're proving the whole consensus protocol, and then you're recursively composing that with previous proofs. Whereas with the Celo approach, you're just doing that for the like client protocol. And so you still trust other full nodes to correctly validate the chain and to make sure that no illegal state transitions could happen. But and again, this is what most protocols do today, and it's an interesting, I think, place to be on the kind of trade-off spectrum for kind of trust and kind of data utilization and just usability.
I mean, I'm curious, when you say that you wanted to reduce data even further, what was your goal? Did you have sort of, I need to be able to sync the chain with a 2G connection or something in mind? Or like, where does your requirements come from?
Yeah, so we're targeting 3G connections. And a lot of the users that we interviewed frequently just turn off their data entirely. So they are so data sensitive that they frequently just keep data off. And so in a world like that, there's really no number that you're trying to hit. You're really just trying to make it be as lightweight as possible, because any and all data is too much. People are turning it off.
In this model, the goal is to have one zero knowledge proof that you download and can verify that you're on the correct chain. But how do you actually get to one proof? And, like, if you're proving the validator transitions, doesn't that still mean you need to have one proof for each epoch?
Okay, that's a great question. So this is, it works like this. So what you have to do in order to verify an epoch block, you have to do a few things. So the first thing you have to do is verify the aggregated BLS signature of this epoch block. And in order to do that, you have to know the current validator set or the public keys of this validator set. So that's one thing you have to do. This is one step that you need to prove. Another thing is actually in BLS signatures, you have to do something called hash to group. You have to transform your message from a sequence of bytes to a group element. And that's something that's usually done with hash functions that are cryptographic hash functions like Blake2, SHA-256. And this becomes pretty expensive when you need to do it on large messages and want to do this in a snark. So what we did there is we built a construction that's a composition of Pedersen hashes to compress a big message where the message would be the validator diff of that epoch block or the validator difference. So what validators were added in this block, which were removed, and this would be the message that we verify the signature for. So we compress this message using Pedersen hashes, which are collision resistant for fixed size messages at least. And then we run a more traditional cryptographic hash function, like 2, and we get to a group element. Okay, so this is the second thing you have to do. So we can do both of these things many times in a single snark proof, let's say n times, and then we get a state transition from block I to block I plus n. So you have a snark proof that verifies these n state transitions. Maybe something that would be interesting to note here is that we do use here one level of recursion, which this pair of curves that we use allows. And this is because the 377 curve that we do the BLS signatures on can actually run snark proofs inside it as well. So we use that curve to prove the result of the Pedersen hashes and the Blake 2 hashes, which allows us to stuff more blocks in the outer curve, in the outer snark. And that's how you get to many VLS state transitions in one snark proof. Maybe I should add that it doesn't have to be one block or one snark proof that the light client downloads, because this thing has finite space, and maybe creating a snark proof that has all of the blocks is too big. So you might have to download 2 or 3.
I see. Do you already know what the practical limitations are? How many blocks you can fit in?
So this is something that we're still benchmarking. This is a bit in flux, but it seems to be in the range of tens to hundreds.
Cool. Yeah, so that would be potentially hundreds of epochs in one proof then. So you aren't like going back to like how you're reducing it. You're going from every header to one header per day to 1/100th of a header per day.
Could be one proof per year, for example.
Yeah.
Yeah.
So these zero knowledge proofs, we've already mentioned Snarks and a couple of things, but what zero knowledge proofs are they?
The zero knowledge proof that we use are ZK Snarks. We actually used the pair of curves that the ZKPs paper introduced. We use the same curves, but in a very different construction than what the ZKPs paper used them for. And the proof system that we use are some of the known ones. So it's gonna be either Bow-Gabizon 18, which is, let's say, a variant of Groth 16, which is simulation extractable. And we're still seeing if we can reduce that to something that has less guarantees and a bit more efficient. But if not, we're good with that.
Are you experimenting at all with like a universal setup, or are you doing a more traditional trusted setup?
So this is something that we're definitely exploring. We expect that for future works, universal setups or universal proof systems will improve the user experience and the trust a lot. So this is something that we would really want to use in the future, and we're exploring to use that in future.
But for now, you haven't actually done a trusted setup or anything. This is just sort of a theoretical thing you're going to do in the future when you deploy this.
Right. So the plan is to port the powers of Tau ceremony that has been done for Zcash sapling. That has two steps in it. So one step is about something that is not circuit dependent, something that everyone that uses the same curves can enjoy and just want to make snarks about in those curves. And the second phase in that setup is creating the proving and verification keys for the specific circuit you want to run. So what we hope to do is to collaborate with the community to do a powers of Tau ceremony for these curves. So if anyone is interested in creating or doing a setup for this pair of curves and is interested in using these sexy curves, and this is definitely something that we would be happy to talk about.
That's a whole new phrase, sexy curves. That's
it's almost as if they planned that.
Yeah.
Yeah, we talked to them about the naming, and it was slightly constructed.
An interesting aspect of the trusted setup here is the danger, and like why people dislike trusted setup so much is obviously it threatens to break the system, right? Like in Zcash, if the trusted setup is broken, then people can mint coins. It's all sorts of disasters on the horizon. If someone breaks the trusted setup of your system, what can they do?
It's a really great question. For good reason, there's a lot of, I think, angst around these ceremonies being done correctly, especially for projects where if it wasn't done honestly, then someone might be able to mint coins in a fully secret manner. Luckily for us, there is always a way to verify the chain without the snark. And so if one were to ever find a proof that claims that a particular header is part of the chain that can be shown is not really part of the chain by performing an actual full node sync, then you will instantly know that the trusted setup was compromised. And so there's some work that Eran Tromer, one of our advisors, has been doing around sharks. And he's really interested in kind of having these proof systems that have the same behavior, where you have a very fast way of verifying a proof and then potentially a slower way of verifying that proof that doesn't rely on a trusted setup. So in his research, he was using bullet proofs for that slower way. But for us, we don't actually even have to use bullet proofs. You can just look at the chain itself and just verify the headers as you would if you were on any other protocol. And so I think that is a very, nice benefit of the way that the protocol is being designed.
Again, this is one of these cases where zero-knowledge proofs aren't being used necessarily for privacy or transaction of tokens, where if something is corrupted, it gets really dangerous or expensive. Here, it's proof of data, the fact that it's there, the fact that it's correct, and the data itself it's public still.
Exactly.
Yeah. And so if a potential attack scenario, I guess, is someone manages to produce a false proof, includes that, then tells someone, hey, I paid you a bunch of money. They like client sync, look, say, yes, it looks like I've gotten a bunch of money. I'm going to give you this product that you bought. And then, it's a falsified block, so they didn't actually get paid and they're out of a product. So it's sort of, you could execute a sort of double spend attack on like a particular targeted user, I guess. But then what you're saying is, if there is at least one full node who is syncing, then as soon as they see that block and try to verify the proof and say that that this thing is wrong, they could sound the alarm and basically tell the community in some way that, hey, this thing is falsified, don't trust this.
Exactly.
So only if it was like payment for a real world asset, where the asset had been transferred over, the payment had seemingly been made at that moment, they can get screwed over, but it will immediately be like flagged.
And only if the trusted setup was compromised. And so the best way to avoid that is, if you are interested in transacting on Celo in the future, participate in our trusted setup and act honestly.
I wonder, could you make, this is just a side, but like given this idea of the universal setup where you have constantly the ability to join a ceremony after it's already kind of launched, meaning like if I want to know for sure that is safe, I myself could join at any time. I haven't seen this yet, but it would be interesting to see where like a zero knowledge proof is being used or a Snarks being used, and at the same time, there's like an option to opt in to this universal trusted setup somehow.
Yeah, I think that's a big selling point for Sonics and for anything that builds on that is the ability to say, hey, if you want to use this system, opt into the security, participate, and you can be safe. But it's, the whole trusted setup thing and zero knowledge proofs in general, I suppose, is an interesting one because there's not been a ceremony that was compromised. So the problem with Zcash, for instance, the bug there was not in the trusted setup. It was in the construction of the thing itself. So it wasn't like the secrets leaked out and they were able to reconstruct things. It was that the thing was wrong to begin with, kind of. So it's in like no one really has any reason to distrust Powers of Tau setup.
That's true. Last week was Blockchain Week in Berlin, and at the Web3 Summit, I did a session, a bunch of workshops. One of the workshops was about interoperability and zero knowledge, and all the ways that zero knowledge proofs could be used for interoperability. And that's actually where the Celo light client was brought to my attention, because by creating these zero knowledge, very light clients, this could potentially help when you're talking about cross-chain communication. Have you guys... Is that part of your thinking? Is this sort of part of your goals with building this?
Absolutely. I think that's a very great side benefit of having an efficient to verify light client protocol, is that you can more efficiently verify it on chain of a separate platform. And so I think, and correct me if I'm wrong, Kobi, BLS 12377, there's a precompile that's potentially slated to land in the next Ethereum hard fork. And so should that be included, it would be possible to verify our like client protocol on Ethereum on chain. And so that opens up a lot of opportunities to build a permissionless bridge between the two chains.
That actually, I mean, this also helped me to better understand. So I had always thought of bridging more in this, I don't know, we'd always learn, when we talked to Igor, I remember thinking of it like it's locked on one side, minted on another. For some reason, maybe we mentioned it, but I had not realized the importance of light clients in that original conversation. But, maybe correct me if I'm wrong, but like for a lot of interoperability, you're not using this light client model. Some of them, I believe, like Polkadot and stuff, are using an overarching model. But are light clients still important in those? Like in the Cosmos network or the Polkadot system, are the light clients still very, very important on the separate chains in order to actually do anything?
Yes, it depends on how trustless you want to go. So in Cosmos, I think if you want to have a quote unquote trustless bridge, I mean, there's still some trust assumptions in there for all bridges, but I think they need light clients. In Polkadot, we are not as resource constrained, so technically you could like boot up a full node that is a parachain and sync using full nodes. But that would be extremely costly way to do it. And so if you have light clients that are easily syncable, then you can embed multiple light clients in one parachain slot. And so bridge like 100 chains in one parachain slot using light clients. So it's still very important.
And the size of them in this interoperability case, like I understood it very much in the case of like Celo specific, where like you want to get it down to that mobile ready light client size. But what about in the interoperability way? Like, if a light client is very, very small, does that actually make the system more efficient? Like where do the improvements actually happen?
Yeah, it makes it more efficient.
Okay.
It makes it so you have to pay less gas to verify the other chain on your chain.
Okay.
So speaking about, going back a little bit to the proof systems that you're using and talking about Geth, where's the code for all of this? What code are you using for the Snarks? Is it like a libsnark thing or the latest Zcash code for it? Or have you built your own thing to like as a prover and verifier?
So what we use is the ZKP code base that has been developed by the Skipper lab. And this is, so most of the cryptography related development happens in Rust. So we built our system or our cryptography related parts of the system on top of ZKP. We have our own Rust crate that implements these BLS signatures and some of the Snark work that we've talked about. That's publicly available online, and this is integrated into Get as a static library that gets linked.
Cool.
And all of it is open source, and you can find it at github.com/celo-org.
Okay, so what's next for the Cellar project? Well, actually, where are you guys at? Like, is it all live?
We have a public testnet that's been out for a while. It's called the Alpha Horus testnet. It's named after a delicious cookie from South America, introduced to us by one of our early community members in Argentina.
Ah.
And we'll actually be naming our next network through soliciting other delicious foods from around the world. So if you know of a great bee food, let us know. And I think bibimbap is a contender right now.
Yeah.
So you got to do better than that. So right now we're auditing a lot of the work. We have 5 different audit firms that are looking at everything from the security of the system to the economics and game theory behind our proof of stake protocol and the stability protocol. And then we're also actually actively formally verifying every one of our system smart contracts and hope to do that by launch as well.
When is launch?
Yeah, and so next up is to release our release candidate network. And on that, we're going to do game of stakes. And so if you're a validator or if you're interested in kind of dipping your toe in that space, then definitely keep an ear out. I think starting in October, or November, we're going to have more news on that front. And then depending on how things go there, we'll be launching at some point soon after.
Cool. Well, listen, thank you guys so much for coming on the show, talking to us about Celo, about light clients, about zero knowledge in light clients, about how a small light client can be awesome and what it can do. Yeah, and good luck with the project and everything.
Thank you. It's awesome being here. Thanks for having us.
Thanks for having us.
And to our listeners, thanks for listening.
Thanks for listening.